In option F.2, or for you higher level students, the core 14.1, we're going to talk about analog and digital signals. And many of you may recognize a lot of this as review from your computer programming days, which may still be going on. I'll pause for a moment while you read the joke and laugh a little bit. Yeah, see, 2 in a row where I'm starting with jokes. We're off to a roll here. Digital signals, as opposed to binary signals, are encoded, stored using the binary system, and it's a system of ones and zeros. Those are binary. That means 2, 1 and 0. While our normal numbering system uses a base 10, we have 0 through 9, which gives us our 10 values, so that's our base 10. In a base 2, we have 0 and 1, so that's our 2 there. That binary system can be used to code any of the numbers that we know. In the base 10 system, a number to the 0th power is the 1s, to the 1 power is the 10s, the 2s is the hundreds, to the 3s is the thousands. In base 2, our 0 power is still 1, but to the 1st is 2, to the 2nd is 4, to the 3rd is 8, so on and so forth. And even though it seems a little limited, with our zeros and ones, we can, as I said, code for anything. You look at our decimals here, and so in binary, 1 would be 0, 0, 0, 0, 0, 0 on to 1. So our only number other than 0 would be this final 1. Decimal for 2 would be 0, 0, 0, 0, 0, 0, 1, 0. Now there's our joke. There are 10 kinds of people in the world, those who understand binary and those who don't. So what it really meant is that there are 2 kinds of people. Although, since I just explained it, it's probably not funny anymore, because if you have to explain a joke, it generally loses its humor value. Not that it was funny before. From there, we can also code for letters and all of our symbols. In our binary system, each of these ones or zeros, is called a bit. And there are 8 bits in a byte. And so you think about our storage systems and hard drives and flash drives, we're talking about gigabytes and megabytes and kilobytes. And so this is what we're really talking about. We're talking about this information that we can store. And when you have 8 bits in a byte, each one of these 8 places then is our bit. And so with that, we can store all of our characters. When you talk about encryption systems and things like that, the 8-bit, 16-bit systems, particularly think about gaming systems and things like that, those systems are talking about the number of places here and how much information. And so when you have a 64-bit system, you have more potential values that you can code for, which means you can have more colors, more shapes, more all of that stuff, because you can have a lot more detail with the larger bits. And so then each one of these symbols then is 1 byte. When talking about our coding system, 2 terms we need to know and remember are what we call the least significant bit, and this is the one that's furthest to the right, and this determines whether the number will be even or odd. And this is going to change frequently depending on any small change in the number. The most significant bit is the farthest to the left, and this is the one that changes the least often. And you often see those far left values, all 0, 0, 0. Those are our most significant bits, and then here's our least significant bit as our 1 there. So how do we convert to binary? Well, let's convert a number just to kind of see how it works. Let's say we have 67, and we want to convert 67 to binary. We have to figure out what is the largest power of 2 that's less than 67. So you go to the first, second, third, fourth, fifth, sixth. Okay, so you get 2 to the 6th. 2 to the 6th is equal to 64. Okay, 64 is the largest number less than our number we're trying to convert. So that means that 2 to the 7th will be 0. 2 to the 6th, that's a 1. So 1 times 2 to the 6th, that's 64. 2 to the 5th times 0, that's 0. 2 to the 4th, that's 0. 2 to the 3rd times 0. 2 to the 2nd times 0. 2 to the 1st, that's 2. Okay, times 1, that's 2. Plus 2 to the 0, that's 1 times 1, so that gives us 1. So we add all this up. 64, 0 plus 64, 0, 0, 0, 0, plus 2 plus 1. That gives us our magic number 67 that we're trying to encode. And so then we write this out. We have 0, 1, 0, 0, 0, 0, 0, 1, 1. And there we have it. That's all there is to it. Pretty straightforward. Okay. If we look at it, I'll just throw a quick example in here. Let's say we have 0, 0, 0, 1, 0, 1, 1, 1. Okay, so we have 0 times 2 to the 7th plus 0 times 2 to the 6th plus 0 times 2 to the 5th plus 1 times 2 to the 4th. Two to the 4th plus 0 times 2 to the 3rd plus 1 times 2 to the 2nd plus 1 times 2 to the 1st plus 1 times 2 to the 0. So we have 0 plus 0 plus 0 plus 2 times 2 is 4 times 2 is 8 times 2 is 16 plus 0 plus 4 plus 2 plus 1, and so 0, 0, 1, 0, 1, 1, 1 is 23. And so you can see also, we mentioned that this last one determines whether it's going to be an even or an odd number, because if this is 1 times 2 to the 0, that's going to be 1, and that's going to make it an odd number. If that's 0, then it's going to be an even number. And when we talk about sending these digital signals, we're talking about signals. All we're talking about really is the transfer of information wirelessly or sometimes with wires from one place to another. And so anytime information is sent using electric fields or electricity or anything like that, that's what we're really talking about when we talk about these signals. And so let's start looking then at the difference between an analog and a digital signal. An analog signal is continuous. Okay, it has basically an infinite number of differing possibilities and value. There's no set value for what it has to be. The time varying feature or variable, whether it's volume or frequency or any type of magnitude, it's a representation of some other time varying quantity. If you think about our analog meters, our analog ammeters and voltmeters, you can, whatever the 0 to the maximum values, you can have any increment along there. You could really almost have an infinite number of different values along that range, depending on the decimal you go to. If we have a circuit where you have some type of variable resistor and a light bulb, as you change the resistance, the brightness of the light bulb is going to change. As the resistance decreases, the light bulb gets brighter. So the signal here, the time varying feature, is the brightness of the light bulb, which is representing the change in the resistance of the resistor. When we're talking about circuits and currents, you generally see this as a change in the voltage, the current, or the frequency, being the most common ones that we use. So the intensity varies over time. You can see it, it could be anything. It could be something like that. It could be, well, that might be a little extreme, but you get the idea. Transmission of sound is a good example of this. When you talk into a microphone and it's connected to a speaker, the voice, or your voice, or the music, or whatever it is that you're talking into, causes very small pressure changes inside the microphone. And there's a little electromagnet, or a little electromagnet in there that starts to oscillate back and forth, and it creates a potential difference inside the microphone. That gets converted to a signal, which is then fed through an amplifier, and the signal, it simply magnifies the strength of the signal coming in. And so you can have any variety of levels in that type of situation. With a digital signal, it doesn't vary, though. It doesn't have a range. It's either on or off. It's one discrete value or another. It's a 1 or a 0. And so in that type of case, if you have a light bulb in a circuit, there's no variance in the brightness of the light bulb. It's either on or it's off. It's a 1 or a 0. It's open or closed. There's no variation in that signal over time. It's one thing or another. It's very discrete, very absolute. Okay, and so the variations are very abrupt. They're very immediate. And so computers use our binary code, our 1s and 0s, to send these digital signals, and they're sent as a series of high and low electrical potential differences. And so you have a high potential difference, that's a 1. You have a low potential difference, that's 2. And when the computer or phone or whatever it is that's receiving the signal gets it, it's important that the receiver understands or knows how many bits are in the signal, so it knows the proper rate at which to read it. And so digital devices have been standardized, and everything you find is going to be in some multiple of 8. And so not only do they have to know the number of bits, they have to know how fast it's coming in, how many bits per second. So not only how many numbers am I reading, that's going to be a specific code, so I get everything right, but how fast are those numbers coming in? If the timing isn't right, it's not going to read every single signal. It might miss a couple, which is, of course, going to throw off the entire. And so what that means is that if, for instance, a signal is sent at 20 kilobytes per second, then each pulse or lack of a pulse, if it's a 0, is going to last 1/20,000th of a second. And so that means that the computer has to read the signal every 50 microseconds. If it reads, for instance, every 100 microseconds, then it's only going to read every other data point or every other piece of data, and it's going to miss half of the information. And so that's why it's so critical that it's reading it at the appropriate rate. And again, as we mentioned, with the clocks and with the timing, it's again critical that the sending signal and the receiving signal are sent and started to read at the right point, so that the information is correct. And sometimes the clocks can get unsynchronized, no clock's 100% accurate, and so what they'll do is they'll send it in blocks. They won't just send one continuous stream of data. They'll send some, they'll resynchronize, they'll send some more, resynchronize, send some more, and so on and so forth. So they maintain that synchronicity and the receiver. And because of this, signals are able, there's a technique that we can use to send information. It's called time division multiplexing, and basically it's sending multiple sets of data at once, or seemingly simultaneously, because it's being sent so quickly. And so if you have two separate pieces of data, we have our red data down here and our blue data down, or green data down here. I'm apparently colorblind today. That data gets broken up and it can be sent at different times. And so because the signal for the red data is going to be broken up anyway, and the signal for the green data is going to be broken up anyway, in between each, they send the other data. So they send some of the green data, then some of the red, then some of the green, some of the red, some of the green, some of the green, some of the red, green, red, green, green, until it's all sent. Because it's going so quickly, it essentially seems like it's being sent at the same time. And the sender simply places a code at the beginning of each block to identify what piece of data it belongs to, where is it going, what is it related to, so that it doesn't get confused or mixed up. And in this now digital world, a lot of our analog stuff is getting converted to digital. And converting from analog to digital is a pretty straightforward process. You simply have to, instead of having this continuous time varying value, which we would see here on the left, we have to determine a number of discrete specific values that we're going to use. And the more of these values, the more storage is required, but the more accurate the representation. If we were looking at, for instance, this piece of data, whatever it happened to be, a piece of music or noise, if we only had, say, 3 values, we have one value here, one value here, and one value here. Okay, this whole signal, which you can see has a pretty significant number of different levels, would be broken up into only 3 different discrete values when it was converted to digital. If we added maybe 2 more, okay, so now we start to get a little bit closer to the actual representation. But then over here, in this case, we have 12 different levels. We have 12 different discrete values that we can use. And you can see that actually there's 11 discrete values because these two at the top are the same. You can see the blocks here are a much better representation. It's like when you take a when you're looking at the area under a curve, right? And if you learned in calculus, you take these blocks and you take smaller and smaller and smaller blocks, and as you take smaller and smaller blocks, you get a closer approximation of the actual area under the curve. Well, here, as you get smaller and smaller blocks, or you add more and more discrete values, you get closer and closer to the actual sound or image or whatever the data happens to be. But on the other side of that, the more values you have, the more storage space that you're going to require, because the more data you're going to have. So it's a trade-off. So then we can take those quantized values and convert them into a binary system using our potential differences. And so if we have ranges from -6 volts to +6 volts, just as an example, then we can represent basically 13 different numbers, 0 to 12. And those numbers can all be used or can all be represented using a simple 4-bit system. Now, once you get beyond that, then we have to go beyond a 4-bit system and obviously add more bits and more bits and more bits. But you can do 12 levels or 13 levels very easily with just a 4-bit system. And as long as the bit rate is known, that signal can then be converted back to a potential difference, which can then be used to drive a speaker or create an image on a computer, or be read by a computer to create an image on the screen, something like that. And then the other part of this is the sampling rate of the analog signal. And so if you have a signal like this and you only measure it every, here and then maybe here and then here, your conversion is going to look like this because all the measurements you took were at the peaks. And so the higher the sampling rate, the more often you take a data point, the more often you take a measurement to get those specific values, the more accurate your final signal is going to be. And there's a thing called the Nyquist theory, which states that for a signal to be accurately converted, it has to be sampled at least twice the frequency. And so if you're sampling it at twice the frequency, that means you're going to get at least one crest and one trough value through the cycle, and that's going to give you a more accurate representation. It's not going to be great, but that's kind of the minimum. Okay, so the minimum sampling rate should be at least double the frequency of the signal. Okay, so let's take a look at this sample here. Okay, and in this case there are 22 samples taken for every cycle. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11-ish. So you have 11 here, you have 11 here. Okay, so the sample rate is basically 22 times the frequency, so that's good. And you can see that you get the general shape. And in this we're using 0 to 15. So we have, so let's look at some of the pros and cons. And if we look at this diagram down here, it really kind of illustrates one of the biggest benefits of using digital versus analog, and it has to do with noise. So if we have an analog source, so we have this right here. When you have noise with an analog signal, so you have something like this gets introduced, you get some type of conglomeration, you get some type of signal that is a mixture of the two, of the analog signal and the electromagnetic interference. And so you get a lot of noise, you get a lot of static and crackling and things like that. But with our digital source, because it either is or it isn't, it is or it isn't, even with a little bit of electromagnetic interference, that signal stays the same. So if you look at what you get, this line right here, it's still a 1. This is still a 0. This is still a 1. This is still a 0. This is still a 1. So when the thing that's receiving that signal reads it, it's still going to read it as a 1 or a 0. So you're not going to lose. You won't lose any clarity in the signal. There won't be any noise. There won't be any of that interference mixed in. It's still going to be a very clear, very clean signal. But of course, with analog, with digital, you don't get the basically infinite number of possible values. Some other points with this: the coding of the signal can easily be changed by changing the sequence, but you can also mess up the coding. It's source independent, which is a big thing. You can send any type of information in a digital format. You can't send you can't send a video on a magnetic tape, cassette tape. You can't send a computer program on a VHS tape. So you can't send a computer program on a vinyl disc, vinyl record. It doesn't work. With digital signals, the signal is a signal and you can send any type of information. With analog, you have to have a specific type of medium for that particular signal. Multiplexing is much easier with digital. That should make sense. Compression and changing the rates has more of an impact on analog. Like for music, if you speed up the rate of the information transfer, you're going to increase the pitch. You're going to change the pitch of it. So just some of the cons. Now within the full system, the full conversion system, you have the analog information put in. The samples are taken and that information is held. It gets converted into the digital signal. It gets transmitted to wherever it's going. You have some other type of converter that changes it from digital to analog, and then you can have some type of output device, some analog output device like a speaker. So the circuitry and all that is fairly complex, but the actual system itself is pretty straightforward. You input the analog information, you take your samples, you convert those samples to a digital signal, you transmit it, that digital signal gets converted back to analog, and then you have it put out into some format that can be read. And there it is. That's all you need to know about digital and analog signals.